Now we're moving into a short segment where we're working with different amines and aldehydes and ketones, essentially. So what happens when we treat an aldehyde or a ketone with a primary, secondary, or tertiary amine? So to start things off, let's just remind ourselves of what it means if an amine is primary, secondary, or tertiary. So a primary amine has 2 hydrogens and 1 R group. A secondary amine has 2 R groups and a hydrogen, and a tertiary amine only has R group, so it has no hydrogen. Why is this going to matter? Well, nitrogen-hydrogen bonds are things that can break pretty easily, proton transfer events, right? NH, like these hydrogens here, are not very acidic, but this nitrogen is currently basic, so it can protonate, and if it's basic, it's also somewhat nucleophilic, so it could actually add as a nucleophile, and once it does that, one of these H's is going to be more acidic, so that would lead to proton transfer events. On the other end of things, if we look at a tertiary, since there are no hydrogens there, we can't break any of these nitrogen-carbon bonds, so that's going to mean that that tertiary amine is probably less reactive than these other 2 types. So we're going to start things out with the reaction of a primary amine with an aldehyde or a ketone. So that's where we're going right now. All right, so we have a primary amine and an aldehyde. It would do the same thing if it was a ketone, but I'll just write up here. We have a primary amine. And what we see is that when you mix these 2, they form this functional group, which is called an imine. An imine. So at this point, we have to ask ourselves, well, how did this happen? What's the mechanism of this? What would cause this to happen? Is this favorable in the forward or the reverse direction? All of those are relevant questions. And it turns out that this is going to be a pretty long and drawn-out mechanism. And what usually helps people when they do these long, drawn-out mechanisms is to really try and rationalize each individual step of the mechanism. And writing things out leads to better understanding and memory of how and why that would happen. So that's what I generally talk about at this point in the class, is essentially breaking each step in this mechanism down and putting like a letter or something by it, and then somewhere else on a page writing out letter A, this is why this happened, et cetera, et cetera. So in any case, we have our primary amine, we have our aldehyde. What's going to happen here? Well, the aldehyde is still the same functional group we've seen over and over again with different nucleophiles. It has a partial positive right here, a partial negative right here, and negative slow to positive. So what is the most negative thing over here? Well, our nitrogen is the most electronegative element. It has a lone pair. It's partially negative. So the partial negative is going to be drawn to the partial positive of this aldehyde or ketone. So that is what I would draw there. And then for A, somewhere on a different piece of paper or on the same piece of paper, I'd write something like a partially negative nitrogen was attracted to the partially positive carbonyl carbon. I'm not going to do that with every step here because it would just make a really long video, but I'm going to say these things, and what you guys should be doing is charting your own situation out here so that you can really try to understand why these mechanistic steps would happen. So, carbonyl carbon. Okay, so what happened there? Now we have our O minus, we have our NH with the CH3 on there, and now we have that positively charged. So what's going to happen next? Well, what happened to the oxygen? People often call this reaction, we're forming an imine, but it's a condensation. What does a condensation mean? Condensation means condensation might form in the reaction. What is condensation made of? Water. We're forming water. So this oxygen is actually leaving as a water molecule. And how might that happen? Well, when the nitrogen adds in, these hydrogens become more acidic. and that can lead to intra or intermolecular proton transfer reactions. So that would happen to make our O minus OH, and then we now have NHR, or in this case, I'm just going to draw a line to the CH3. So why would step B happen? You might want to try and rationalize that yourself. B, what happened? Well, let's break this down to just an acid-base chemistry step. Well, what is O minus like? O minus would be like HO minus. And then what is this nitrogen moiety like? Well, that would be very similar to NH4 plus. What's on the other side of this acid-base equilibrium? Well, that OH minus is going to grab one of those protons, so that would form NH3 and H2O. Well, why would this step happen? Well, what side is favored in this equilibrium? The pKa of NH4 is around 9. The pKa of water is around 16. So, in that case, why did step B happen? Step B happened because this was a downhill acid-base transfer step. So, it makes sense that transfer would occur. What else is in the reaction? Well, we also have some weak acid around. Weak acid is usually H3O plus. So we have some H3O plus around. And let's draw that with the proton being able to transfer easily in a mechanistic sense. So at this point, we have our water that was our leaving group. Where did that come from? Well, that acid could protonate that OH. C, why would this step happen? And essentially that generates our OH2 good leaving group. Our nitrogen is still there the same. Why would C happen? Hold on one second, I'm going to make some more room. So step C, let's analyze that acid-base equilibrium. Well, we have essentially an alcohol, so we'll just call it ethanol, because this is an alcohol, and we have H3O plus. So what side of this reaction would be favored? Well, H3O plus would likely have a pKa of around negative 1.7. If we transfer that proton over here, we still have basically something that looks a lot like H3O plus. So the conjugate acid over here is an oxygen with 3 bonds and a positive charge. Its pKa would have to be roughly the same, negative 1.7. So why did step C happen? Step C happened because acid-base reactions have really low activation energy barriers, and we formed something that's essentially the exact same energy level as what we started with. So that's what happened here in step C. And now we have a really good leaving group. Water is a great leaving group, and it turns out that it can just leave. If it did that, we would have this carbocation be what was formed here in this reaction mechanism. D, why would that happen? Well, water is a good leaving group. Good leaving groups want to leave. Water did not want to retain that positive charge. It wanted to be neutral. And when it leaves, it is neutral water, H2O. That's a really stable molecule. What about this carbocation? That doesn't look like a very stable carbocation at first glance, but something is stabilizing that. What is stabilizing that carbocation? Yeah, it's not just on that carbon. It is stabilized by resonance. This nitrogen has a lone pair. It can donate that lone pair for us to see the separate resonance structure that demonstrates why it might be relatively stable. It's not just a carbocation there, it's a carbocation on 2 locations. And this is the more prevalent resonance structure since everything has an octet. We said we have weak acid weak acid often refers to, we don't have a full equivalent of acid, we just have catalytic acid. And whenever we have weak acid that's acting as a catalyst, we have to reform that acid in the last step. So we use the acid here. Catalysts are used in a reaction, but then they're reformed in the reaction. So the water that was formed in this catalyst step could be floating around as well. Here it is over here. And how do we form our imine in the last step? Last step is just a proton transfer to that H3O plus. Why did step D happen? Step D happened because water is a good leaving group. This would be step E. Why did step E happen? Well, we have weak acid around. That's a catalytic acid, and in a reaction we use that and we reform it. So we had to reform it somewhere. There it is. So that's the last step. That forms our imine. Let's talk about the blank on the bottom of your course packet for this page. It says that the reaction is an equilibrium. And essentially what that means is that it can be driven to one side or the other just based on concentrations. So while in some reactions I draw single-headed arrows, like this goes directly to this, to this, to this, whatever, what you'll notice in this mechanism is that all of these arrows were equilibrium arrows. And that was really intentional. If we took this aldehyde and we swamped it with a lot of this amine, say that there's 10 of these amines for every one of these aldehydes, that's going to push the equilibrium in this direction. That's Le Chatelier's principle. If we swamp the imine with water, we add a ton of water to the reaction, that's going to push the reaction the other way. So that's what I mean when I say reaction is an equilibrium. It can be driven by a high concentration of reactants or products. So you add a lot of this, it would push the reaction to this side. You add a lot of water, it pushes the reaction to the opposite side. So that is how imines are formed. And it's going to be really, really similar to how the next, how secondary amines react with carbonyls. So if you understand this mechanism, and hopefully you wrote out all the different steps and why things likely could occur, the next reaction should be very straightforward as well. So look forward to that. All right, so we just saw how imines are formed with primary amines, and now we have a secondary amine here with our aldehyde, and again, this could be a ketone. And what we see is we form this functional group. What would we call this functional group? Well, we have an amine, right? That's an amine. Looks like a tertiary amine. And this is an alkene. Alkenes we call enes. This is an amine, so together we call this functional group an amine. And enamine. Enamine. So enamines are formed essentially by the exact same mechanism as imines, except for the last step is a bit different. So I'm just going to draw some equilibrium arrows. And we say A, B, C, D, E. And once we went through all of those same exact steps as what we just saw with an imine, we would have this, we would just go A through D. We would have this intermediate, right? And what happened in the last step with an imine? In the last step with an imine, one of these nitrogen bonds was a nitrogen to a hydrogen bond. And like I said at the beginning of this video, we can't break nitrogen-carbon bonds the same way we can break nitrogen-hydrogen bonds. The proton transfer reaction for NHs is really fast, but it's slow. We don't break a nitrogen-carbon bond. So how can we get from here to the stable enamine, the neutral enamine? Well, we note that we have one hydrogen here and we have two hydrogens here. So what must happen? The same situation that happened last time. Last time we had water deprotonate the NH bond to reform our catalytic weak acid. This time, since that nitrogen no longer has a hydrogen, that oxygen instead has to deprotonate the hydrogen that is alpha to that carbon-nitrogen double bond. So that is the last step in providing the imine to enamine transformation. And we actually refer to this as an iminium ion. So en route to an enamine, we form an iminium ion, and then the final proton transfer, instead of getting us to an imine, gets us to this enamine. So again, same exact mechanism. I want to focus on steps A through D are the same. The last step still happens because we need to generate, so this is step E, we need to generate that catalytic acid back, but it's just that the carbon-hydrogen bond is deprotonated this time instead of the nitrogen-hydrogen bond. So that's the only difference here. Last thing about carbonyls with amines, we saw primary amines form the imine, secondary amines form the enamine. In your course packet, it says tertiary amines have blank with aldehydes or ketones. That blank should be filled with no reactivity. We have to have that nitrogen-hydrogen bond for productive reactions to occur. Since tertiary amines have just nitrogen-carbon bonds, they cannot produce products the same way that secondary or primary amines do. So that's it. That's all of the amine reactivity with carbonyls, or not with carbonyls, but with specifically ketones and aldehydes.